Today I'm going to tell you kind of a long story with multiple different parts. I'm going to start by talking about trigonometric functions, which is a standard topic, very traditional, and then I'm going to go through some other stuff. And I do have a goal in mind, which is to solve this crazy looking integral. But I do want to talk about these other things first, because if I just start the video now and just solve the integral, um, probably what's going to happen is that you may understand what I'm doing, but you're going to be left with that uncomfortable feeling with, I would have never thought of that. So I don't want you to feel like you understand what I'm doing in the integral, but you yourself would not have had the tools to think of it. So this is why I want to talk about other things first, okay? It's going to be multiple parts, and sometimes you may feel like it's disconnected from the topic. Feel free to skip some parts if you want, but just know that what I'm trying to do is to contextualize, because when I solve an integral like this, it's not just the integral itself. I'm leaning on all of the other stuff that I know. So I chose some things to talk about today in order to contextualize a little bit. How is it that I think to solve this integral in the way that I'm going to solve it? So how do I think of that? Let's start by talking about trigonometric functions. I have here the sine function, which starts at 0 and then periodically goes up and down. It has a period of 2 pi, because whenever we talk about trigonometric functions, we will be measuring all angles in radians, and this 2 pi comes from the unit circle, where you have gone around the circle one full time, so that's 2 pi radians. And the maximum value of the function is 1, the minimum is -1, and again, this is because of the unit circle, because this is how far up and how far down the point can go as it goes around the unit circle. But this topic begins to be interesting when we do graphic transformations on this function. So I'm going to start by giving it a vertical translation. I've done +5 here, but of course it could have been any number. And a vertical translation is when you take the graph of the whole function and you just shift it up without doing anything else. So it doesn't become bigger, it doesn't stretch, rotate, or anything. It's just the same graph, but higher up, in this case by 5 units. And this is something that you can do for any function, of course, it doesn't have to be trigonometric, but in the particular case of trigonometric functions, what happened is that it was originally oscillating up and down around the x-axis, which is the line y = 0. So now that it's shifted up, it is going up and down around this other horizontal line, which is the line y = 5 in my example. And this line is called the principal axis of the trigonometric function. So when you're given a trigonometric function like this one, for example, and you want to figure out what the principal axis is, then you just have to look for what was the vertical translation that happened on the original trigonometric function, which in this case was +5, which makes the principal axis of this function y = 5. But the original function was going up and down by 1, right? So starting at y = 0, going to 1 and to -1. I've just translated it up. There was no stretch going on yet. So going around the y = 5, it's going to go from 4 to 6. If I want to change that, if I want to keep it going around the 5, but say that instead of 4 and 6, I want it to be going from 3 to 7, so twice as big, I can do that by a vertical stretch. In this case, a vertical stretch by scale factor 2, which is what happened in the purple function here. Notice that if I were to take the 4 and the 6 that I had on green and then multiply that by 2, it wouldn't be 3 and 7, right? It would be 8 and 12. But the thing is that even though I talked about the vertical translation first and then I talked about the vertical stretch, what's happening when you say 2 sine x + 5 is that the vertical stretch is the one that's happening first. That's because of the order of operations, because it's 2 times sine of x and then +5. So multiplication has priority over addition. So what happened was that the red function first was stretched, so it was going between -2 and 2, and then it was translated up by 5. Okay, that's how it ended up going between 3 and 7. And the last thing that I'm going to tell you here before this picture gets to be too much and I have to start a new one is that we know that sine of 0 is 0. That's by thinking about, again, the unit circle. So the sine function originally started at 0 and it starts by going up. But when you're talking about trigonometric functions and allowing for these graphic transformations, the function is not always going to start at 0. If you look at the purple function, for example, it's starting at 5. So the way that you are going to recognize a sine function and distinguish it from a cosine function is not that you're going to say that it's starting at 0, but what you need to keep in mind is that the sine function starts at its own principal axis, which is the case of the 5 here. So it starts at the principal axis going up. That's how you recognize what is a sine function. The cosine function is different. I'm going to draw it in a minute. It starts at its local maximum. But you could also be seeing a function that starts at the principal axis and goes down instead of going up, like the pink function there. It's like the purple upside down. So this is a vertical reflection, which is also a graphic transformation, which means that the number that is multiplying the original function is actually a negative number. And these are all the vertical graphical transformations that can be happening in your trigonometric function. You have the translation that changes the principal axis. You have the vertical stretch, which changes something that's called the amplitude of the trigonometric function. Amplitude is also an interesting word for you to know. And just know that the amplitude is the distance vertically between the maximum of a function and its principal axis, okay? It's easy to get confused and think that the amplitude would be the difference between the maximum and the minimum, but that's not the case. It's the distance between the maximum and the principal axis. If you want to say that it's the distance between the principal axis and the minimum, that's okay as well because the axis is in the center, right? So it's the same distance down as it is up. And also be careful here. Don't say that the amplitude is -2 because it's not. The amplitude is 2. It's just that in the case of the pink function, there is a negative sign there because it has suffered a reflection. So that means that instead of starting at the principal axis going up, it starts at the principal axis going down. Cosine functions also suffer these same transformations, and the way that you recognize one from the other in the graph is by looking at whether it starts in the principal axis or it starts at a local maximum. For example, the red function here has a principal axis at y=4, and it is starting at the principal axis, so this is a sine function. This is 2 sine x plus 4 because 4 is the principal axis and 2 is the amplitude that goes from 4 to 6. Here is 2 units. But the green function is not a sine function. The green function is a cosine function because it starts at 12, which is its maximum, and its principal axis is at 10. So I know that it is the function 2 cosine x plus 10 because 10 is the principal axis and 2 is the amplitude, which is the distance between 10 and 12, or if you prefer, the distance between 8 and 10. And what about the purple function? The purple function is not starting at the principal axis, so it can't be a sine function, but I want it to be a cosine function, but it's also not starting on a local maximum. It is starting at a local minimum. The maximum is up here. So if it starts at a local minimum, it's because it is a cosine function upside down, which means that it suffered a vertical reflection and it's going to have to start with a minus. In this case, it's -2 because the amplitude is 2, which is the distance between 3 and 1, and +1 is because of the principal axis that is at 1. But I also want to talk about the horizontal transformations that these functions can suffer. In this picture, I haven't written anything down on the horizontal axis yet, so you can't know what is the period of this function. But what you do have to know is that the period of the function sine of x by itself, this period is 2 pi, because that's how long it takes to go around the unit circle once. So in an exercise like this one, when you're trying to figure out what the expression for the function is, the numbers 4, 7, and 10 are already telling us everything that we need to know about the vertical transformations. But as for the horizontal transformations, you're going to have to look for some numbers on the horizontal axis. For example, if you have this number here is 5, and this corresponds to this point in the graph, when the function has just finished doing once the thing that it's going to be repeated, then you know the period of this function is 5. Not every exercise of this type is going to be as straightforward as this. Sometimes they find a different way to tell you, for example, the distance between two consecutive local maximum. That's also a period, right? But the more creative they are in how they tell you what the period is, the more difficult the question becomes. I've chosen a very simple one because I just want to tell you what to do with the period of the function. In this case, we already know the amplitude is 3 and the principal axis is 7. But the fact that the period is 5 and not 2 pi means that we're going to have to multiply the x by something that I am temporarily calling b here, because multiplying x by a number is what makes a horizontal stretch, okay? And the important thing to keep in mind in horizontal graphic transformations is that they do the opposite of what you would expect them to do. Of course, I've already mentioned this in other videos talking about transformations of functions that were not trigonometric. But it's the same thing here. For example, if you do f of x plus 4, then it's going to the left instead of going to the right. If you do f of 2x, instead of making the thing bigger, you're actually making it smaller. So f of 2x is a horizontal stretch of scale factor a half. So it's 1 over 2. And here as well, this represents a horizontal stretch of scale factor 1 over b. So if your period is 5, and it used to be 2 pi originally, but then it suffered a horizontal stretch of scale factor 1 over b, then you have 5 equals 2 pi over b, which is how you're going to figure out what b is. So it looks like that, and you would have done it in the exact same way if it was a cosine function instead of a sine function. Regardless of the numbers here or here, that doesn't matter. The horizontal thing is completely separate from the vertical thing. And the main thing that you need to know in this type of exercises is that period is equal to 2 pi over the number that multiplies the x in your expression. And it's very common to end up having a pi here, okay, like in this case. That is because the original period has a pi in it, so it's very common that the answer for b will have a pi. Not always, of course. I'm just saying it's common because sometimes people see that pi there and they imagine that it's too complicated, it must be wrong. And I'm trying to tell you that not necessarily. So it's very common to have a pi in the b. But the most annoying transformation that you have to think about sometimes is the horizontal translation. And I don't want to talk about it too much because the fact that it's more annoying than the other ones also means that it appears a lot less in exercises, okay? So I'm just going to tell you what it is, and I'm not going to focus on it too much. We just have to know that it exists, really. So here's the first example, x plus pi over 6. So that's pi over 6 to the left, and sine of pi over 6 is a half. So when x is equal to 0, the function is going to be sine of pi over 6, which is half. So that's why this is annoying, because now you look at this graph and it's not starting at the principal axis. We wanted our sine functions to start at the principal axis going up, but now because it has shifted to the left, I mean, it is starting at the principal axis, but the start is not quite at 0, so it gets everything confusing. It gets even more confusing when you want to do a horizontal stretch and a horizontal translation on the same function, like this red one that I'm about to draw. So it's sine of 2x plus pi over 6. The 2x is going to make a horizontal stretch of scale factor a half, so it's going to become half as big. But notice that when x equals 0, you're still getting the same value, sine of pi over 6, which is half. So the red function is also going to have that same y-intercept. And this is even more annoying because a lot of the time when they are giving you the function, they will add this extra parentheses here. So it's like factoring out a 2 from the way that I had originally written my example. And it's the same function, of course, but now there is a pi over 12 here that you don't immediately see relating to the 1/2 over there, which is the y-intercept. I mean, of course, you can see it by putting x equals 0. So it's going to be sine of 2 times pi over 12, which is pi over 6, and the sine of pi over 6 is a half. But there is this extra step in the middle. So you can see it, but it's not as immediate as if it was written like this. And all of this confusing stuff happens for kind of the same reason as the confusion about the x-axis that has always been there. The fact that adding 2 makes you go 2 to the left, the fact that multiplying by 2 makes you become smaller. It also messes with the order of operations, because when you say 2 times x and then plus pi over 6, it looks like the priority would be the multiplication. So you would do the stretch first and then the translation. But that's not really what's happening, at least if you remember how I did the blue picture. First, I shifted it to the left by pi over 6 and put the y-intercept there, and then I scaled it down by a half. So if you write it down this way, and please bear with me, this is far from obvious. I am just telling you what happens. Then it is the stretch that is happening first, as it should be, because of the priority of the order of operations. So the stretch is happening first, so it's becoming smaller, and then it's being shifted to the left. So then it's not going to be shifted by quite as much. It's going to be shifted by pi over 12 instead of pi over 6 because it's already smaller, so just half of that. And that works. It produces the same picture, but it's really annoying. So like 90% of the time, the questions are not going to involve the horizontal translation, like this one that has every other transformation except for the horizontal translation. This is really common, okay? And other than just the simple look at this picture, identify what the function is, a lot of the times the IB questions about this topic will have a little context, a little story, but in the end, they're just asking you to figure out what the function is. What is the value of A, B, and C? Like in this example here, they describe this as a Ferris wheel, which has a diameter of 110 meters. And it starts 10 meters up from the ground. The function h of t describes the height from the ground of the point P as it goes around the Ferris wheel. So it's that height over there, which of course changes with time as the P is going around the wheel. When it's up here, it's going to be a bigger value. And the story that is described in the problem says that the P starts here. It starts at its lowest point. So remember, who starts at its lowest point? Well, it's cosine. Of course, the problem is already telling you it's cosine, but it's cosine when it's upside down. So from that information, we already know that A is going to be a negative number because it's starting at the lowest point. But it's negative what number? It has to be the amplitude. So how much am I going up and down? Well, the diameter of the thing is 110, and the lowest point is at 10, which means that the highest point is at 120. Function is starting at the lowest point and going up to the highest point, so which means it's oscillating around a principal axis that is the midpoint between these two numbers, 65, which is then the value of C, and the amplitude is the distance between the principal axis and the lowest point, which is 55, which is the radius of the Ferris wheel. So if I remember correctly, this question was 5 marks, and this is already 3 of them. The next 2 are for figuring out the value of B, which is the horizontal stretch, which has to do with the period of the function. And I forgot to tell you that the question told us more information, that it takes 20 minutes for the Ferris wheel to go around one full time. So the period is 20 minutes. And we already know that the period needs to be equal to 2 pi over b, which means that b is pi over 10, and that's it. That's the end of the question. So another thing that I want to point out is that sometimes in the middle of a larger question, you will need to find the minimum value of this trigonometric function. It could have been the maximum as well. And a lot of times, understandably, people get confused by seeing the word minimum, and their mind immediately goes to this must be an optimization problem, so I must find the derivative of the function and set it equal to 0. This is not wrong, but it's a lot more than the question requires, because it's not an arbitrary function that we're trying to find the minimum value of. That's what calculus is for. But this case is not an arbitrary function. It's a trigonometric function. We know a lot of stuff about this trigonometric function. It has a horizontal stretch and translation, which are going to have zero effect on finding its minimum value because they are horizontal transformations and the minimum value is a vertical thing. All that you need to know here is that sine of whatever it is, 5x minus 7, still the sine function goes from minus 1 to 1. So the minimum value is minus 1. So in this case, the answer to the question, find the minimum value of this function, is just negative 10. And this kind of confusion happens also in another universe, has nothing to do with trigonometric function, but here's a quadratic function. If somebody asks you to find the minimum value of this function, again, some people immediately jump to calculus. I'm going to find the derivative and set it equal to 0. It wouldn't be that bad in this context because the derivative is quite easy. But again, you don't have to do that because it's not an arbitrary function. It's a quadratic function. You know a lot of things about quadratic functions. In particular, you know that its minimum value is the y-coordinate of the vertex. So all that you need to do in this exercise is first find the x-coordinate of the vertex, which is easier, turns out to be 1, and then you apply the function to that value to find the y-coordinate of the vertex, which is 2. So there you go. That's the answer to part B here. The minimum value of this function g is 2. These are not calculus questions. So these are the basic graphic transformations that exist, the ones that we've been exploring. But I also really like to do some other things graphically, like adding one function to another function, for example. This kind of thing will allow you to quickly do a rough sketch by hand, provided, of course, that you're adding functions and you know what each one looks like individually. In this example, I have the function x, which is the red one, and the function 1 over x, which is the blue one. And now when I want to make a sketch of one plus the other, what I need to think about is this plus this is a number for each value of x. So I'm going to think of adding it vertically. In this case, I'm going to start with the red one and think of adding the blue one on top of that. So as x is getting bigger, the blue function is getting very small. So I'm going to be adding almost nothing to the red function. But it's an almost nothing that is still a positive value. So the new function is going to be bigger than the red function. On the other hand, when x is closer to 0, then blue is getting very big, and it's actually the red one that is quite small. So when you think of one plus the other, because blue is so much bigger than red, it's going to be almost the same thing as blue. In between these two parts, I can see a point here where they intersect each other, which is a point where both values are the same. So when I add one to the other, I'm getting twice that value, which is a point roughly here, twice as big as that one. And then I can just connect the dots. I can do the same thing on the left side, but now all the values are negative. So when I'm adding the blue on top of the red one, it's actually a small value but negative. So the green will be under the red, and the same thing here on the right side, and in the intersection it's this value plus itself, and then connect the dots. So there you are, kind of an interesting function, this green function. It has a vertical asymptote and it has a diagonal asymptote. Here's another interesting example. We are going to start with x to the power of 2, which is just this parabola here. And then I want to add to that the sine of 10x. I chose 10 as a big number to make the period very small, to make it oscillate quickly. And this oscillation is not going to be happening around a horizontal principal axis because it's being added to a parabola. So it's going to be oscillating over this curve, something like this maybe. I'm not really taking into account the scale of the things, okay? 10 is just an arbitrary number that I put here. So I don't really know how many times it would go up and down before we stopped seeing the difference between the green and just the quadratic function, because at one point the quadratic function is going to be going up very, very fast. So we're not going to be able to see this oscillation anymore. Anyway, I'm not interested in that. I'm not thinking about the scale precisely. It's just a very rough sketch to understand what kind of picture a certain function should have if it is adding two functions that I know. Here is a very nice example of the kind of exercise that can be solved using this type of idea. I wish that more people would look at something like this and think of a method of solution that involves drawing a sketch, rather than thinking that this is going to be algebraic. I'm going to put an equals k here and then try to solve an equation. There's too much stuff going on there for you to be able to algebraically do anything useful with it. There's a square root, there's an absolute value, there is something plus something else, and they both have x. This doesn't look like something very convenient for algebraic manipulation. On the other hand, when you think of drawing a sketch, it is just one function plus another function, and one of them is very easy. It's just a function y equals x. The other one is not as easy, but you can handle it. So let's try this approach. First of all, here is the graph of just the function square root of x. This is one of many functions that you have to know. So its domain is from 0 to infinity because you can't take square roots of negative numbers. And it has kind of this shape, which is the top half of a parabola that has been placed sideways. The bottom half would be here, but that's not part of the function. And it looks like that because the square root of x is the inverse function of x squared. But in this problem, we don't just want the function square root of x. We want square root of the absolute value of x. And that is going to change its domain, because the problem with the square root is that you can't have square roots of negative numbers, but the absolute value of x is not a negative number because it's an absolute value. So when you are on the right side of the sketch, that is the same as this. Having the absolute value on a positive x doesn't change anything. But then when you move to the left side, the absolute value of those numbers are these numbers. And please notice that I am turning my hand around. I am not sliding it this way because this is a reflection. It's not a translation. So now that I've added the left side, I can say that the red picture is the square root of the absolute value of x. And at least if you're an IB student with AA high level, I hope you've seen this before, because the transformation of horizontal absolute value is part of your syllabus. And you should know that the right side remains unchanged and the left side becomes a reflection of whatever is on the right side. So the other function that I want to add this to is the function y equals x, right? And it's this blue line here. So I want to take a look at the point of intersection, which is the point 1, 1. We all know that the square root of 1 is 1. Of course, there's another point of intersection here at 0, 0. But I also want to look at the reflection of this point on that side. So I want to look at the point negative 1, 1. That point is interesting not just because it is the reflection of this naturally interesting point, which is an intersection, but that point is also interesting because in the same x coordinate of negative 1 on the other function, I have a minus 1. So when I add both of them, 1 plus negative 1, that's going to be a 0. So that place is interesting because it's going to be 1, 0 of the function that we're interested in sketching. Of course, the other 0 is here because both functions are 0 at x equals 0. And in between these two zeros, we have to know that our function is positive, because for values of x that are less than 1, or rather between -1 and 1, the square root of the number is going to be bigger than the number itself. So this is like the square root of 1 over 4 is 1 over 2. So between this point and this point, we are adding a positive number to a negative number, which could go either way, but the positive number is bigger than the negative number. So this is positive. On this side, I'm adding two positive numbers, so it looks like this. Of course, it should be a 2 here because it's 1 plus 1. I'm just not having enough space to draw it with a proper scale. And to the left there, now it's going to go below 0 because now I'm adding a negative number that is bigger in absolute value than the positive number that I'm adding it to. So it's there. And finally, we should look at what the question wants. It wants values of k such that this equation has exactly 3 solutions. This equation, the function being equal to k, is equivalent to passing a horizontal line somewhere, which is the value of k. I'm trying to compare the green with the purple now, and clearly for this value of k, green function equals to purple k only has one solution, so that's not what we want. If k was 0, it would have two solutions, which are the two zeros. That's also not what we want. We want three solutions. So three solutions we have here, for example. 1 in this final increasing part, 2 and 3 in that left side over there. So that happens not for k equals 0, but for any k bigger than 0 until k reaches this point here, which I'm going to call P, okay? So for P, which is that local maximum there, I have the local maximum and this other point here on the right side. There are two solutions to F equals K, but that's not what I want anymore. So it's K bigger than 0 and less than P. So in order to finish this question, now I want to find the value of P, and for that I'm going to use calculus. I'm going to take the derivative and set it equal to 0. But before I take this derivative, I want to stress two things here. Yes, this one was a calculus problem, unlike a couple of other problems that I already solved in this video. But knowing calculus is not enough to solve this problem. You also need to have this intention of solving a problem by drawing a sketch instead of by doing everything algebraically, okay? If you don't go through that intention and that idea and the skill of actually producing the sketch, then the calculus is not really going to help you that much because you're not going to know what you're looking for. And the second thing that I'm going to point out is that never, ever, ever do I want to take a derivative of a function that includes an absolute value, because the absolute value function looks like this. It has a sharp corner. The function is not differentiable at that point. The derivative is constant equal to 1 here and constant equal to -1 there. Just a clunky function to work with, and I don't want to do that. Instead, I'm going to take the derivative, and I know that the point that I am looking for has a negative value of x. So I'm just going to work with that part by saying for x less than 0, and then I've traded the absolute value for a minus x, because minus x is what absolute value of x is doing on the left side. If it was on the right side, I would have just said square root of x here. And please, please, please don't be tricked by this negative sign here into thinking that I am taking the square root of a negative number, because I'm doing the exact opposite of that. X is a negative number because I am on the left side. And if x is a negative number, then minus x is a positive number, which is exactly the kind of number that I am allowed to have inside of the square root. So anyway, now I'm just going to take the derivative. I'm going to need the chain rule here because the minus x is composite function inside of the square root. So this is the derivative. I want to set it equal to 0 to find the value of x that has that local maximum over there. Here are the steps to solving that equation. The answer is -1/4, which is a negative value like we wanted. And just to wrap up the problem, we still needed the value of p. P is f of -1/4, which just plugging into the function gives us the value of 1/4. Here is another problem that goes along somewhat similar lines. This one is more explicitly supposed to be a calculus problem because it gives you a function and asks you for the minimum value. But again, it is a function that involves absolute values, And like I've just said, I never ever want to take the derivative of that. So before I do anything involving derivative at all, I am going to make a rough sketch of this with what I know about these functions. So if it wasn't for the absolute values here, this part would be a parabola. It would be quadratic and the zeros would be 0 and 2. So if I was just sketching a quadratic function, the next thing that I would do would be to ask whether the concavity is up or down. But in this case, because of the absolute values, it's neither, or you could say it's both, right? It is whatever the concavity needs to be so that that function is always above the x-axis, because absolute value is positive number times another absolute value, which is a positive number. So this always has to be positive. And this function looks like this. I even marked the vertex there because it was sort of easy. So in blue here, I'm putting this part, which is just the function y equals x. The next thing that I'm going to do is to graphically add red with blue to make a green function. And for now, I'm ignoring completely the -2 because the -2 is just a vertical translation. That is not going to change where the minimum point of the function is. So I can ignore the -2, find out the value of x for which the function has its minimum value. And then when I'm looking for the actual value of it, which is what the question wants, then I can remember the -2 again. So let's add these two functions. I have included the point 2, 2 here on the blue line because there's a 2 here, so I probably want to know what happens there as well. And this intersection point is 1 for the red and for the blue. So when I'm drawing one plus the other, then it's going to be 1 plus 1 is 2. 0 plus 0 is also 0, making a green point here. I want to connect the 2 points, and I am not particularly worried about whether it's going to go up fast or slow or where the maximum point is going to be, because the question is not about a maximum point. The question is about a minimum point. But anyway, for x equals 2, I have 0 plus 2, which is again 2. So in order to connect the dots, I probably have a local maximum around here, but again, not interested in it for this question. After the 2, what's going to happen is that this red part is positive. So if I'm thinking I'm adding that to the already positive blue part, then it's going to keep going more up, and that's also not going to make a minimum point. Now I have to see what happens on the left side. Because on the left side, I am adding a positive number to a negative number, so it could go either way. The question is whether these red positive numbers are bigger than these blue negative numbers. So I'm just going to look at the red part of the function and just for x less than 0, because now I don't need the absolute values anymore. I can just work with this function, and you can check that if x is less than 0, then this is less than 0 and this is also less than 0, which means that one times the other is positive. So that matches what we see in the picture. So I've done distributive here to make the derivative easier. And the thing that I want to notice here is that this derivative is less than -2 because x is less than 0. At the same time, the slope of the blue line I know is 1 because that's the line y equals x. So in other words, in the left side where we're interested, the red function is going down faster than the blue line is going up, which means that the positive numbers that we see here are actually bigger than the blue negative numbers. And so this plus this is a positive number. It's going to be, the green numbers are smaller than the red numbers because I have subtracted the blue, but they're still positive, which means that the minimum value of the function that we wanted happens at this point for x equals 0. Now I have to remember that I do have the -2 here, so the answer to this question is that the minimum value of g is -2. Multiplying two functions that you know very well can also result in an interesting sketch. Here, I am taking a sine function which has the oscillation between -1 and 1, and I'm multiplying it by x squared, which is this parabola that I also know very well. So if you look at this product as being something that oscillates not between -1 and 1, but it's going to oscillate between minus x squared and x squared, then x squared is already in the picture. Maybe we want to put minus x squared in the picture as well, which is a vertical reflection of this one. And again, I'm using the large number 10 here just to make the oscillation very fast so we can see it. But the green function, which is the product of these two, is going to be something that oscillates between this blue and this red. Definitely a nice sketch to know how to do by hand. And the graphic multiplication can also be used for very interesting things, such as learning what the graph of the secant of x function looks like. And you should probably know that secant means 1 over cosine. And also, this is technically division, not multiplication, but it's the same idea. The fact is that I am going to look at some very specific values of x, see what happens to the function and 1 over the function at those values of x, and then I'm going to connect the dots. So the first thing that I should notice is that 1 over cosine, I am not allowed division by 0. So whenever the cosine function, which is this red one here, has a 0, that point is going to be outside of the domain of secant. And that happens for quite a few values because the cosine is a periodic function, so it has infinitely many zeros, which means that the secant function has infinitely many points that are outside of its domain. All of these points here, they are going to be outside of the domain of secant. They are going to end up being vertical asymptotes, which is why I drew them this way. Now, the next set of interesting points that I want to look at are the ones where the cosine is equal to 1, because 1 over 1 is just 1. So at those points, the secant is going to have the same value as the cosine. That's all of the local maximum that the cosine function has. And if you think about it, the same thing is going to happen at the local minimum, because the local minimum of cosine function have value -1. And 1 divided by -1 is again -1. So those minimum are also points that belong to the graph of the secant. Okay, that's not a lot of dots to connect. But if you think of the asymptotes as also being dots, in a sense, to connect, then this is all that we need. Because we're going to start at this value of 1 here, and then as the denominator of our function, which is the red one, the denominator is getting smaller, then the function needs to be getting bigger. And as the denominator goes to 0, the value of the fraction is going to infinity. That's why this makes an asymptote. So we have all of these asymptotes. The graph of secant is amazing. It has an interesting range, by the way. What is the range of the secant function? It's from -infinity up to -1 closed, and then it stops for a while and then starts back up again here from 1 also closed all the way up to positive infinity. So the next thing that I want to tell you today is that I absolutely hate the integral of cosine squared. The way that I originally learned how to solve this when I was first studying calculus was to split it as cosine times cosine and then work by parts, where you get to this expression, and now you're supposed to use the Pythagorean identity to rewrite sine squared as 1 minus cosine squared. The next step is to separate this integral in two integrals. The first one is easy because it's just the integral of 1. And the second one is meant to make you feel like you're going nowhere because that is the exact same integral that you wanted to solve in the first place. But there is a brilliant trick that is going to happen here now, which is that I am going to add this integral to both sides of the equation here. And now I can just divide both sides of this equation by 2, and that's the answer. So although I have to admit that this is a brilliant trick, it feels very uncomfortable to me. I really don't like it. And it's not really because of the trick itself. I do like the trick. But I find it annoying that this very commonly occurring integral takes so long to solve. It's just an annoyingly long process. And it also feels a little bit uncomfortable to me that at no point during this process did the plus c constant have a chance to appear. I think that's weird. But recently I've started solving this integral whenever I need it by a different process. And this different process starts by remembering the double angle formula for cosine, which looks like this, and then using the Pythagorean identity on this sine squared. We can now distribute this minus sign here and put the two cosine squareds together. The idea is now to add 1 to both sides and next to divide both sides by 2. So now we can use this to substitute for cosine squared up there. And I know that a lot of people have that transformation memorized by itself, but I just don't. So I personally go through all of these steps every time that I need that. And now that's an easier integral to solve, isn't it? Because we can use a simple substitution of u is equal to 2x here, and then the integral of 1 is still just x, but this time the plus c did appear because I have finished my integral. And finally, by using the double angle formula again, but this time for the sine of 2x, now I can cancel this 2 with this 2, and I found the same answer that I had found before. So when it comes to the complicated integral that I actually want to solve, of course, when I look at that, the sine of 2x is the first thing that stands out to me, and I think of using the double angle formula there. Now, even if not exactly that, but we do know that something like that is going to have to happen because there is no way that we can integrate something that has both sines of x and sines of 2x, which are different things, and they are together in the same function. So in order to integrate that, something is going to have to change into the other something. But I did try to start by just using the double angle formula here, and I just went nowhere. I'm not going to go through the steps of the failed attempts. I'm just going to tell you that there were many of them, and I'm going to show you the one that finally worked, which was when I tried not to go the way that it immediately looks like it's asking to be done, which is to use a double angle formula, but instead go the other way and look at this sine of x plus cosine of x and try to bring that back into something else. Now, there is no immediate formula that I know that becomes sine of x plus cosine of x. If it was sine of x times cosine of x, then I would be thinking of the sine of 2x double angle formula. But there's nothing like that for sine of x plus cosine of x. So what did I try to do? Just add the two functions by hand. So in red here we have the sine function, and in blue we have the cosine function. I've just done one period of each of them from 0 to 2 pi because everything else is just going to be a repetition of that. And let's go ahead and add some special points that we can see. For example, for x equals 0, we have 0 plus 1 is 1. For pi over 2 as well, it's this 0 plus that 1, which is equal to 1. Same thing happens here, of course, at the end of the period. And as for the ones that are going to be negative 1, we have this 0 plus negative 1 here, and 0 plus negative 1 here. Other interesting points that we can think of to look at are the intersection points. And when is sine equals to cosine? Well, that happens for x equals pi over 4. Both the sine and cosine of that angle are the square root of 2 over 2. So when you add both of them together, you just get the square root of 2, which is a little bit higher than 1. It's like 1.4, so let's put that in the picture. And I've connected the dots like that over there because of symmetry, okay? I know that that point of pi over 4 needs to be the maximum of the green function that I'm drawing because of symmetry. It looks the same here and here, so yeah, that's the only way to connect the dots. And something similar but on the negative side is going to happen here, where the minimum is at negative the square root of 2. Now this dot is going to connect to this dot by going through 0 at 3 pi over 4, which you can see because you know that the sine of 3 pi over 4 is the same as minus the cosine of 3 pi over 4. I know that I'm just saying these numbers, but if you draw the unit circle, these things are much more obvious. And similarly, 7 pi over 4 is the other 0 over here. This finishes one period, but I don't want it to look like a local maximum, so I'm going to dot, dot, dot here to make sure it looks like it continues. Okay, so what kind of function is that? The principal axis is still at y equals 0, but the function is not starting at a local maximum or at a local minimum, and it's not starting at the principal axis. So there has been a horizontal translation that happened here. I get to choose if I want to treat it like a cosine function or like a sine function, but either way, I'm going to have to deal with that unfortunate horizontal translation. I'm going to go with cosine. Lucky for me, at least it has the horizontal translation, but it does not also have the horizontal stretch, which would make it a lot more difficult. I know that it doesn't have a horizontal stretch because the period is still 2 pi. So if it was a cosine function, it would have had to start here, but it didn't. It went pi over 4 to the right, which means that I want to put x minus pi over 4 here. Does not have a vertical translation because the principal axis is at y equals 0, and the vertical stretch is by a factor of square root of 2. Okay, so I've put that into the integral, and before I move on, I want to make sure that I prove something here because I hope you are questioning what I just did. I took a trigonometric function and I graphically added it to another trigonometric function. I've made some points which were calling out to me, like the specific points that were interesting. And then I connected the dots as if I wanted the results to also be a trigonometric function. And I acted as if I know that it is, but I didn't actually prove that. So I want to take a moment here to stop and prove that this is actually always the case. When you take one trigonometric function and add it to another trigonometric function, you're always going to get as a result a third function that is a trigonometric function. And then, of course, you have to think about what the transformations are. But this is always true. Here's an example. And the two functions do need to have the same period in order for this to work, but everything else can be different. In fact, I am not going to be using these vertical translations here because we might as well just add 9 in the end, and that's not the interesting part. The interesting part is to look at our two cosine functions as the real part of two complex valued functions. And by the way, this particular application of complex numbers is part of the AI high level syllabus, but is not part of the AA high level syllabus, which I find very interesting because this is not really applied. This is a very math. It's just math. Anyway, we can rewrite these two complex valued functions in their Euler form and then add these two together. And now I don't want to say that the next few steps are obvious because none of this is obvious, but it's like I feel that there are natural steps when you don't really know what you're doing, you don't know where this is going, so why not? Let's distribute this I over here and this one as well. And now why don't we split this minus this into two powers of the number e that are multiplying each other? This can be interesting because now you have an e to the I for x that can be factored out. And here's the thing, I've just picked out random numbers for my example, so there was no reason to expect it to be a doable calculation in the end. But the point is that this part inside of the parentheses is a constant. Everything that used to depend on x is in the part that has been factored out. And this will always have happened by this point, regardless of which numbers you're using in your example. There is a part that depends on x, but that has been factored out because it was the same for both functions, given that I did say that they need to have the same period. And then that's multiplied by a part that is a weird complex number, but it's just a constant complex number that does not depend on x. I'm just calling it REI theta. And like I said, this is part of the AI syllabus, so you're going to have your calculator with you at all times anyway if you want to do this in general. So don't worry about how to find the values of R and theta, okay? The point here is that they are constant values. And now we are going to go backwards. We are going to put these two parts back together again like this and get this out of Euler form and back into polar form. But remember that the complex numbers weren't really in the problem that we were trying to solve. They're just a tool that we're using behind the scenes here. What we really wanted was to add just the real parts of those two numbers, which are the two cosine functions. So if you add the real part of two complex numbers, the answer to that needs to be just the real part of the complex number, that is the addition of both of those. And this is another cosine function like we wanted. So if you take two cosine functions and you add them together, sure, you're going to have a different amplitude and you're going to have a different horizontal translation here, but your period is going to remain the same and you're still going to be a cosine function. Okay, so now that we've done that, it doesn't really feel anymore as if the double angle formula is the best bet here, because it would be looking at that sine of 2x as a sine of x plus x. The double angle formula would give me a sine of x and a cosine of x, but I don't even have a sine of x and a cosine of x anymore. I have a cosine of x minus pi over 4. So I want to do something that is similar to that, but is not exactly that. So instead of writing 2x as x plus x, I wrote it as x minus pi over 4 plus x plus pi over 4. And the reason is that instead of using a double angle formula now, I'm going to use a compound angle formula, which is this formula that looks like this. And I'm going to use the a and the b as this pink and this blue thing here. Okay, so this looks very big, and it also looks a little bit concerning because I've been trying to make all the sines and cosines be of the same thing, and I haven't really done that because some of them are x minus pi over 4 and others are x plus pi over 4. I'm going to deal with that in a minute by using this equality here. But before I do that, I just want to take the next step in the integration, which is going to be to choose a substitution. So this is the substitution that I'm going to use. Notice that this derivative does not actually require the chain rule because the derivative of this is just 1. So if I put this dx over there, then I can see that this part is here, which is going to become my new du. This part here is u, and I'm going to leave that one there for a minute because it's going to be easier to deal with it later. Okay, so take a look again at the functions sine and cosine together. As you know, they are the same, just changing where they start. So that means that one of them is a horizontal translation of the other. You can look at it as the sine being the cosine that was shifted to the right. It was shifted by pi over 2, which going to the right means that we subtract pi over 2. But that is not quite what we want because we want a plus pi over 2 here. So we should look at this blue function here, is what happens when the cosine is shifted pi over 2 to the left. And notice that the blue function is just the red function upside down, which means that it is minus sine of x, so vertical reflection. So minus sine of x is what happens to cosine of x when it is translated pi over 2 to the left, which is what's happening here. But instead of happening on x, it's happening on x minus pi over 4. So that this thing here is minus sine of x minus pi over 4, which is going to be a lot more convenient for us because this is the substitution that we've been doing. So this here is minus u. And now I want to do something similar for this other factor that I've circled in purple here. X plus pi over 4 is x minus pi over 4 plus pi over 2. And the sine function, which is the red one here, when I take it plus pi over 2, that means shift it to the left by pi over 2. So when I shift the red one to the left, I get to the green one, which is cosine, which means that this term here is the cosine of x minus pi over 4. So let's make these substitutions. The orange one is going to become minus u. So it's going to be u times minus u. I'm putting the minus u squared all the way to the left here. And then the purple one is the cosine of x minus pi over 4, which is multiplied by another cosine of x minus pi over 4. So that's a cosine squared. Now I can put this together with the u substitution that I'm using there. Cosine squared is 1 minus sine squared. So this here is 1 minus u squared. Can put some things together here. 8 plus 1 is 9. And then I have 2 of the u squares. And this is exactly the type of integral that I solve by partial fractions. I'm not going to bore you with the details here, but a and b both turn out to be the square root of 2 over 6. And then just to organize things a little bit, this minus can go up here. The square roots of 2 all cancel out. Can use a log minus another log to make it look a little bit more pretty. And then, of course, don't forget to substitute back u for that. Now, if you've tried to solve this problem yourself before watching my solution and you made slightly different choices along the way, you may have come up with a different answer, but that wouldn't be surprising because we've been talking about this sine and cosine. They are just horizontal translations of each other. So if you end up with a cosine of a different thing to compensate, that is very likely still the same function.